a little overlap here between AP Psychology, of all places, and AP Chemistry. Intrapersonal skills is how a person sees themselves and relates to themselves. So this cat sees himself as a lion. Intramolecular forces is how the elements in a molecule relate to themselves, so how a molecule relates to the elements in it. So ionic and covalent bonds, or polar molecule. Those are intramolecular, the things that keep those elements together in one cohesive molecule. And that was the focus of our last unit. This unit is going to be on intermolecular. Intermolecular forces are the forces that hold one molecule to another. Just like interpersonal skills are how you relate to your peers. It's an intermolecular love story. It's an attraction between one molecule and another. We'll often abbreviate this as IMF, standing for intermolecular forces. And like all good love stories, opposites will attract. These forces arise from an unequal distribution of electrons, meaning that one side is positive and one side is negative. But does not mean that a molecule always must be polar, having a positive and negative end. We'll see some cases where a molecule adopts that setup based on the people it's around. Intermolecular forces are forces that condense matter. And anytime you want to uncondense matter, you have to overcome these forces. So solids would have the greatest intermolecular forces, holding them in place, giving them only vibrational motion. They can only vibrate back and forth. Liquids would be the next up. If you break some of those intermolecular forces, break them apart a bit, you end up with a liquid. And if you overcome them completely, you end up with a gas. The strength of the intermolecular forces is what determines how low a boiling point is, or how high a boiling point or melting point is. The lower the boiling point, or vapor pressure, or melting point, the weaker the intermolecular forces. And the opposite is true. Higher boiling point means higher intermolecular forces. So think of it like people. The better a couple is, the more in love that they are, the more energy it would take you to be the evil mean girl to break them apart. Or boy, if you're a homewrecker. Moving on. The strongest intermolecular force, or IMF, is dipole-dipole. This is an attraction between two polar molecules, where the positive or partial positive end of the polar molecule is attracted to the partial negative end of another polar molecule. Remember that a polar molecule are those that have an unequal distribution or an uneven charge, since they have a dipole moment, meaning there's a higher concentration of electrons around one end of the molecule than on the other. Compounds exhibiting dipole moment have extremely high boiling points and melting points, higher than those that exhibit weaker intermolecular forces. Now, there is a special type of dipole moment that happens when you have a hydrogen bound to an oxygen, nitrogen, or fluorine. A hydrogen bound to an oxygen, nitrogen, or fluorine has its nucleus extremely exposed to other electrons around it. And if it sees another oxygen, nitrogen, or fluorine on an adjacent molecule, it can form this, I use air quotes, partial bond. It is not an actual bond, it is an extremely strong attraction. So again, the hydrogen must be bound to a nitrogen, oxygen, or fluorine, and there must be an adjacent nitrogen, oxygen, or fluorine that it can be attracted to. Now notice that with water, I can have two hydrogens having this extremely strong attraction for this oxygen. Why is that? Well, this oxygen has two lone pairs of electrons around it. If you draw the Lewis structure for water, you'll see it has two lone pairs on the oxygen. Those two lone pairs are extremely attracted to the hydrogen, to the bound hydrogen in an adjacent water, and it forms this hydrogen bond, which is actually the strongest of all the intermolecular forces. So while it is a special type of dipole-dipole, a molecule that exhibits this type of bonding will have higher boiling points, melting points, than molecules that only exhibit dipole-dipole intermolecular forces. So when you're comparing the boiling points and melting points and the intermolecular forces of two compounds, you want to compare ones with similar number of electrons. Because since all molecules have electrons and these electrons are in constant motion, they're going to repel one another. However, they're also going to be attracted to the protons of another molecule, or of that molecule. And so you want to only compare between molecules that have similar number of electrons. So here we have a list of many different halides, or halogens, or it's not halogens, halides. So wait a minute. Hydrogen, hydrogen-containing compounds, all with similar number of electrons. Carbon and 4 hydrogens, that's 6 plus 4, that's 10 electrons. 4 valence electrons and 4 electrons is 8. 5 and 3 is 8. 1 and 7 is 8, and 6 and 2 is 8 as well. And as we see in this trend here, there is a gradual decrease in the boiling point as we move up the period, because we have less and less electrons as you're moving up in period 4. But when we get to, so we would expect to see a similar trend in the next family over with the halides. However, as we move, with the halogens. However, once we reach fluorine, we see that there's a colossal jump in the boiling point. What is that jump from? It's from a hydrogen bond. Same with group 5. It's gradual decrease till we get to nitrogen. Nitrogen has the ability to form a hydrogen bond. With the chalcogens, gradual decrease. When we get to oxygen, massive increase, because oxygen has the ability to make 2 hydrogen bonds. Not bonded pairs, but 2 hydrogen bonds that are contributing to its intermolecular forces. So nitrogen, oxygen, and fluorine have extremely high electronegativity values, which causes the hydrogen, oxygen, nitrogen, or fluorine bonds to be extremely polar, which means that their attraction is very strong. They also form very small molecules. Nitrogen, oxygen, and fluorine have very small molar masses, and this allows those dipoles to be closer together, which further strengthens those bonds, or further strengthens those intermolecular forces. Attractive forces dissipate with increasing distance, so if they can get very close, they're going to be very strong. A weaker intermolecular force is ion-induced dipoles and dipole-induced dipoles, in which a nonpolar compound, in the presence of a cation or anion, so an ion of some sort, or a dipole, can adopt a dipole-like configuration. In this case, the cation with the positive charge is going to attract the electrons in the nonpolar molecule and make them cluster on one side, giving what was a nonpolar compound a dipole, because you'll have an area where there's a large concentration of electrons, an area where there's a less concentration of electrons. It will disturb the orbital of the electrons, and it will form this partial negative and partial positive. The ion induces a dipole. Same thing holds true when a dipole induces another dipole. You have a polar compound that forces or makes another compound behave like a polar compound. The positive end of this dipole is going to attract electrons from the nonpolar compound and disturb its normal electrons orbits or orbitals, and cause an area of greater concentration on one pole and an area of less concentration on the other, making it partially negative and partially positive. You can think of this also in terms of people. You have a friend, and he's usually a pretty cool guy. He's not much of a douchebag. But then he meets someone, and he likes them so much that when he's around them, he behaves a little differently. And you think he's a bit of a douche. But when that person leaves, he goes back to being pretty normal. That person is inducing or forcing them to change. So this is a weaker type of intermolecular force. Ion-induced dipoles are stronger than dipole-induced dipoles. The larger a molecule is, the more polarizable it is. So smaller molecules, since they have less electrons, are going to be induced less, or have less of a distribution, a less unequal distribution of their electrons than something that is massive. The weakest of all intermolecular forces is the induced dipole, or Landon dispersion forces, which we'll abbreviate LDF, or dispersion forces. This is when, since electrons are free to move around the nucleus in any which way they want, if at any given point they all cluster to one side randomly, they would cause a partial pole, on a partial negative on one end of the atom, or the molecule, on one end of the molecule. And this would cause a partial positive on the other end of the molecule. They, in fact, will induce their own dipole. And it happens in a nano of a second. And this forces other molecules around that nonpolar atom to adopt the same polar configuration. And it's a momentary, instantaneous attraction between these temporary, extremely temporary poles of one molecule and another. Notice that I avoided using the term van der Waals. If you're taking AP Bio, you'll hear van der Waal forces. Please, for the love of God, never talk about van der Waal forces. When you're talking about them in AP Bio, you're talking about this. However, it is an excessively abused term, and in AP Bio, you'll use it to discuss dipole. You'll use it to discuss dipole-induced and ion-induced. So saying van der Waals on the AP test for chemistry will not score you any points, while it will for the AP biology test. Do not use van der Waals in this class. We will call them Landon dispersion forces or dispersion forces. Personally, I find induced dipole too long to say. So again, it is an instantaneous temporary dipole that occurs when all of the electrons, due to random movement of electrons, cluster on one end of the atom, or on one end of the molecule, and provide a temporary dipole. This forces the other molecules around it to also adopt a temporary dipole. The more electrons a molecule has, the greater the likelihood of this temporary of this sporadic occurrence. All of these forces, all of the intermolecular forces, are a function of the number of electrons in a given molecule and how tightly those electrons are held. Now, one word you're going to want to write in large quantities on this AP test and on the AP test when they ask you about intermolecular forces is polarizability. Since molecules have electrons floating around them, and since the molecules are constantly moving, when they collide, the electron cloud of one molecule is going to distort the electron cloud of the other. This produces a momentary or temporary dipole within the molecule. The amount that the electron cloud is distorted is what we call its polarizability. And since now that molecule has become polarized, it has a positive end and a negative end, it will attract other molecules around it. Now, the more electrons a molecule has, the greater the polarizability, because there are now more electrons that can be thrown from one side of the molecule to another. This is the reason why iodine is a solid, bromine is a liquid, and chlorine and fluorine are both gases. Chlorine and fluorine both have very few electrons, so their polarizability is rather low. Whereas bromine has 70 electrons. That means there's a lot of electrons going to be swashed back and forth and back and forth. Smack into one, you're going to make them all turn polar. So it can form a liquid at room temperature. Iodine with 106 electrons has a ton of electrons flying around it, and therefore, if you smack into it, it's going to become extremely polar, and it will form a solid at room temperature. Polarizability, big word of the month.